Hey guys, welcome back, and we're going to jump into 2.10 inverses of exponential functions. So we've got this graph over here on the side, and it's an exponential function, and it's 2 to the x. So if I look at these points here, so I can see this point is at -1, 5, 0, 1, 4, 3, 8. I record those points over here as values of x and y. So the first point we looked at was at when x is -1, y was 0.5. When x was 0, f of x was 1. When x was 1, f of x was 2. When x is 2, f of x was 4. And when x was 3, f of x was 8. So if I'm looking at this, I notice that the base here is 2. And I can see that this is an exponential function because if I look at my x values, as we go from every x value, we're adding 1. But as I look at the y values, I can see that those are increasing not by adding a value, but by multiplying. And not surprisingly, they're multiplying by a value of 2. They're doubling every time. This tells me when the x values are increasing by adding and the y values are increasing by a multiplication, this is an exponential relationship. So let's talk about what that idea of an inverse is. Remember that an inverse is a reflection over that x comma y point. So if I just go ahead and just really quickly draw this in the line where x equals y, 1, 1, 2, 2, 3, 3, and so on. It'll look something like this. This is my line x equals y, and if you have an inverse, it will reflect over that line. So if I look here, I can see that the reflection of this 0, 1 will be at 1, 0. I'm going to put this in purple. Be at 1, 0. The reflection of -1, 0.5 will be 0.5, -1. The reflection of 1, 2 will be 2, 1. The reflection of 2, 4 will be 4, 2. And then the reflection of 3, 8 will be 8, 3, which is off of my page. So it's going to look something like this. So what do we notice about this? So we notice a couple of different things. So if I look at my original y equals 2 to the x exponent right here, I see that there's an asymptote here as we go off to the side. We can see there's a horizontal asymptote here. Whereas here, its reflection, it doesn't have a horizontal asymptote, it has a vertical asymptote here, okay? So if I go ahead and mark where those points were, when x was 0.5, y was -1, when x was 1, y was 0, when x was 2, y was 1, when x was 4, y was 2, and the inverse of that would have been 8, 3. I look at this and I notice that my x values are multiplying by 2, and my y values here were adding by 1. This is how we can see that this is a logarithmic representation or a logarithmic relation when the x values are being multiplied consistently by the same number and the y values are consistently adding. So you can see that they're opposites. So exponential is adding the x's, multiplying the y's. Logarithmic is multiplying the y's but adding the x values. We can also see that these two reflect their points onto each other because they are inverses of each other. Okay. If you also wanted to check this in your calculator, you could say that the y value will equal the log of whatever the x value is over the log of 2. And you can see what those values look like. So let's talk about what the big ideas are about inverses of exponential functions. So number one, the graphs are a reflection across the function. So we saw that here in the graph. We saw that it reflects across the function y equals x. The domain, or the x values of the exponential function, is the range, or the y values of the logarithmic function. So let's look back up here. So if I look at the domain of my exponential function, I look here and I see, oh yeah, they are the same as the range of my logarithmic function. The range, or y, of the exponential function is the domain, or x, of the logarithmic function. And we can see that here as well, that the range of my exponential is the same as the domain here. The operations undo each other, just like multiplication and division undo each other. Exponents and logs will undo each other as well. We talked about that yesterday. And then just like before when we learned about inverses, that their compositions of each other, f of g of x should equal g of f of x, which should equal a simple x. And this is the definition of inverses. And we've seen this before as well. So let's jump into example number one. It says describe f of x as an exponential or logarithmic function. So remember how we talked about before, if it was exponential, the x values were adding, the y values were multiplying. If it was logarithmic, the x values were multiplying, the y values were adding. So let's look at what's going here. These x values look like they're increasing by 1 every time, so they're adding by 1. And these y values actually look like they're multiplying maybe by 3 every time. This points to an exponential relationship, okay? And if it is exponential, its inverse, which we'll put here, remember, so we're going to swap the x and the y and the x. So negative 1, 1/3 would look like 1/3 comma negative 1. 0, 1 would look like 1, 0. 1, 3 will look like 3, 1. 2, 9 will look like 9, 2. And 3, 27 will look like 27, 3. We can show that this is also logarithmic because those x values are multiplying and the y values are adding. So we know that this is logarithmic. And then we want to know how. So let's write how we know. So we know this is exponential because the y's are multiplicative, meaning they're multiplying every time. And then, of course, its inverse is the log. Let's look at example number 2. So let's study the values on the x's. So I look at 1/4, 1, 4, 16, 64. These actually look like they're multiplying by 4 every time. And if I look at their y values, they look like they're adding by 1 every time. This tells me it's not exponential, but this is logarithmic. And it's logarithmic because the x values are multiplicative. Okay, so now if I'm going to look at the points for the inverse, just like before, x comma y is going to inverse as y comma x. So 1/4 comma negative 1 is going to be negative 1 1/4 as an inverse. 1 0 is going to be 0 1. 4 1 is going to be 1 4. 16 2 is going to be 2 comma 16. And 64 and 3 is going to be 3 comma 64. And of course now, because it's swapped, we know that this is exponential. All right, let's go to the next page. So let's talk about these inverses and how they undo each other. So here at the top, we're going to be looking at 2 to the x, which is an exponent, and log base 2 of x. So when we're talking about how inverses undo each other, just like we said, okay, if I know that this is exponential, The way that it would be undone is if we apply a log of the same base. Say it with me. Say same base. So if this has an exponential base of 2, it will need to take a log base 2 to undo it. What happens here is log base 2 of 2, you can check it in your calculator, actually is equal to 1. And 1 times anything is just itself. What's left is just x. So this is just simply equal to x. Same thing here. If I have log base 2, that can be undone by an exponent of 2. And so the way that we would say that is we would write this as 2, and make it a power log base 2 of x. So if I have an exponential base of 2 and raise it to a log base 2, these will cancel and we get an x. Okay, they undo each other. So how can we prove that these are actually inverses of each other? So we're going to use the same definition of inverses. Remember that f of g of x should equal g of f of x, which should also equal the value of x and nothing added. Okay, so let's verify to make sure that this works. So how do we find f of g of x? So f is 2 to the x power, where instead of x, we're going to use g of x, which is log base 2 of x. Well, we just learned that 2 to the log base 2 cancels, and we end up with just x, so that's a good indicator. Let's go ahead and evaluate g of f of x. So g of x is log base 2 of x. And instead of x, we're going to plug in f of x, which is 2 to the x. Of course, we just learned log base 2 of 2 will cancel because they have the same bases, and that will also leave me x. So since these are both x, we can say yes, they are inverses. Okay, so let's look at example number 3. It says find the inverse of each of the following. So just like we've been finding the inverse, remember the first step to the inverse is always number 1, to rewrite it so that y equals whatever f of x was. So I can see that f of x is right here. So we say y equals 3 log base 5 of x. The second step is we're going to swap the x for the y. So wherever you see y, we're going to replace it with x. Wherever I see x, I'm going to replace it with y. So to find the inverse here, I'm going to say x equals 3 log base 5 of y. Step 3 is you're going to isolate the y. Okay, so in order to get this y by itself, we're going to start to undo what's attached to it. So multiplied by 3 means we're going to divide both sides by 3. So we end up with x over 3 equals log base 5 of y. We know that the opposite of a log base 5 is we're going to make it a power 2 of 5. So both of these, so this is now 5 to the x to the third, or x over 3, equals 5 to the log base 5 of y. What that does for you is it's going to cancel this out. So we're left with 5 to the x over 3 equals y. So we've got that y by itself. And then the fourth step, of course, is to rename it so that it looks like the inverse. So this is actually the inverse of f of x. Okay. So let's do that again on example number 4. So again, we're going to replace this with y equals 10 x over 6. Now to find the inverse, we're going to swap x and y. And now we're going to isolate x. So in order to get this y out of the exponent, we do need to take the log of both sides. So we're going to take the log base 10 of both sides because that will cancel out that 10. So I'm left with log base 10 of x equals y over 6. Get y by itself, let's multiply both sides by 6. And we get y equals 6 log base 10, or common log of x. Again, we don't have to restate the base of 10. And then y is actually, we know, is the inverse of f of x. So we can say f of x is 6 log x. Also, you should know anytime you have a coefficient in front, this can be also written, oopsie, 2, here we go, log x to the 6th power. These are identical. A coefficient of 6 in front of the log is identical to a power on the log after its variable. So either one of those is fine. All right, so let's try these two. Go ahead and push pause and try them on your own and then check in back with me. So go ahead and push pause and try it. All right, we're back. Let's see if you got the same thing as me. Let's determine if these are inverses. So again, if they're inverses, let's find f of g of x first to see if it equals x. So f is 5 to the 4x, but instead of x, we're going to use g of x, which is 4 log base 5 of x. Here, unfortunately, they don't have, this 4 and this log have different bases. So if I multiply this, these becomes 5 to the 16 log base 5 of x. I can simplify this by taking that coefficient, like I told you before, and putting it up here as an exponent. So this will become 5 times to the log base 5 of x to the 6. The idea is if we can get this base 5 and this numerical base 5 together, we can cancel them, and we're left with x to the 16. So even though it did simplify down, we do not get x as our answer. Therefore, I know that they are not going to be inverses. And I don't even have to move on because unless I got x, there's no point. And what you got, it says find the inverse. So again, you're going to identify where the y is, rewrite it, and then we're going to swap them. So x equals 10 log base 2 of y. Now we're going to isolate the y. Let's divide both sides by 10. So we get x over 10 equals log base 2 of y. To cancel out that base 2 log, to get the y by itself, we're going to make it a power by the 2 on both sides. So 2 to the log base 2 will cancel, so we're left with y equals 2 to the x over 10. This y is actually our inverse. Okay. All right, hope you got it. I'll see you back in class.